From the Discovery of Global Warming by Spencer Free online. Roger Reville, Ocean CO2 and Nuclear Radiation Research for the U.S. Navy following World War II. Before scientists would take greenhouse effect warming seriously, they had to get past a counter-argument of long standing. It seemed certain that the immense mass of the oceans would quickly absorb whatever excess carbon dioxide might come from human activities. Roger Reville discovered that the peculiar chemistry of seawater prevents that from happening. His 1957 paper with Hans Suess is now widely regarded as the opening shot in the global warming debates. This essay not only describes Reville's discovery in detail, but serves as an extended example of how research found essential material support and intellectual stimulus in the context of the Cold War. 1. For other case studies of funding, see the essay on funding Keeling's measurements and the experimental Greenland ice drilling site. For general observations, see my reflections on the scientific process as seen in climate studies. In the mid-1950s, not many scientists were concerned that humanity was adding carbon dioxide gas, CO2, to the atmosphere by burning fossil fuels. The suggestion that this would change the climate had been abandoned decades earlier by nearly everyone. A particularly simple and powerful argument was that the added gas would not linger in the air. Most of the CO2 on the surface of the planet was not in the tenuous atmosphere, but dissolved in the huge mass of water in the oceans. Obviously, no matter how much more gas human activities might pour into the atmosphere, nearly all of it would wind up safely buried in the ocean depths. Links, full discussion in the oceans. There was a hidden flaw in this argument. It was discovered as an indirect consequence of work at the University of Chicago by Willard Libby and collaborators, scientists who had given the question scarcely a thought. In the mid-1950s, they were busy with an exciting new technique, the use of radioactive carbon-14 to find the age of ancient materials. The origins and motives of this technique were diverse, and so therefore was its support. The Chicago group was funded chiefly by the university and by a foundation dedicated to supporting anthropology and archaeology. A crucial auxiliary technique, the enrichment of carbon isotopes, was developed because the isotopes were useful for medical research. But as was usually the case in nearly every field of post-war science, a substantial part of the support was indirectly related to the Cold War. Libby acknowledged that he was also indebted to the Air Force for a contract for the development of low-level counting techniques during 1949. The Air Force had negligible interest in the dates of Egyptian mummies, but it had a hearty concern for delicate radioactivity measurements. One likely use was detecting residues from Soviet nuclear bomb tests. As Libby discreetly remarked, Chicago people built up expertise in measuring radioactivity in other connections. The separation of isotopes was likewise under investigation for military as well as civilian uses. Thus carbon-14 research could incorporate more highly developed techniques than would have been available for archaeology alone. 2. Oceans. Meanwhile Reville was studying, as usual with collaborators under an ONR contract, the results of a May 1955 test of a nuclear depth bomb that the Navy and deck had exploded a few thousand feet underwater. His team found that the radioactive residues had spread out in remarkably thin sheets, stretching 100 square kilometers but only a meter thick. Many years later Reville recalled his surprise that the water from one layer doesn't exchange with the water from another layer. It was one more example of how the huge resources of government nuclear programs made novel observational methods and data available for many kinds of research. In a 1955 report using the depth bomb test data, Reville's group concluded that radioactive wastes introduced into the upper layer might remain there for many years, and would be diluted by a volume of water only a 50th to 100th the volume of the ocean. 17. The same would apply to almost anything else introduced into the upper layer, including CO2, a compound for which the Navy and deck had no interest whatsoever. The oceans. Reveill, however, was getting personally interested in the gas. He had heard the lonely voices of G.S. Callender and Gilbert Plass, who were arguing that if CO2 ever did accumulate in the atmosphere, it would have a strong greenhouse warming effect. Not long after Reveill took up the problem, he began to say publicly that it was possible there could be great and perhaps harmful effects as early as the end of the century. 18. Meanwhile, he and Suess began to apply carbon-14 methods to the question of how the oceans take up CO2. The opportunity for such research was plain to other scientists too. Craig, in close touch with Reveill and Suess, undertook similar calculations with some variations in the equations and assumptions. Independently, James Arnold of Princeton in collaboration with Ernest Anderson of the Los Alamos Laboratory developed another variant of the research. They were following up their recent interest in tracking radioactive materials such as bomb fallout. Arnold and Anderson were soon exchanging ideas with Craig, Reveill, and Suess, and all agreed to publish papers simultaneously. 19 CO2 greenhouse. Reveill, Suess, and Craig all acknowledged funding as usual under contract with the Office of Naval Research. This was a general contract to Scripps, covering a number of research projects, driven partly by various potential applications and partly by pure scientific curiosity. For example, in his July 1956 progress report to the ONR, Reveill mentioned the CO2 studies in connection with measuring ocean turnover. He went on to report that Craig had spent most of his time that spring working on the question of ocean disposal of radioactive wastes. 20 Anderson, at Los Alamos, was supported by the EC. He could justify travel for discussions with Craig and Reveill, he wrote, because of their interest in the waste disposal problem. This is, of course, for Los Alamos' benefit. 21. His collaborator Arnold drew support from a more obscure source, the U.S. Army's Office of Ordnance Research. The Army officers were willing to fund research on abstract nuclear theory and geochemistry, and neither Arnold's proposal nor his reports hinted at any link to ordnance. If I wrote an open proposal, Arnold recalled, and the Department of Defense chose to support it, and didn't make me get a Q, top secret, clearance and work with them and whatever, it was fine with me. 22 The studies by Arnold and Anderson, Craig, and Reveill and Suess all used much the same research plans and data, and came to much the same conclusions. As Reveill and Suess put it, the average lifetime of a CO2 molecule in the atmosphere before it is dissolved into the sea is of the order of 10 years. 23. Further, all three studies used carbon-14 data to estimate that the oceans turned over completely in several hundred years. Given the leisurely time scale that most people assumed for the future growth of industrial emissions, that seemed fast enough to swallow up extra CO2. CO2 greenhouse, yet there remained Callender's insistent claim that measurements of CO2 in the atmosphere showed a marked increase. If he was right, one way out for Reveill and his colleagues would be to assume they had not taken proper account of how forests and other biomass took up carbon. The magnitude of that process was so poorly known that it would allow fudging the numbers. I am not too happy about the whole thing, Suess remarked. 24. CO2 greenhouse. The draft calculations by the three teams had all addressed mainly the steady-state rates of exchange between atmosphere and ocean. But the crucial question for global warming was a transient effect, the net flux of new CO2 into the water. And as Reveill knew from the carbonate chemistry problems he had been rethinking since the Bikini Atoll studies of 1946, seawater is hypersensitive to change. To match an increased level of CO2 in the atmosphere, the number of CO2 molecules in the water would rise only as one factor in a cascading readjustment of the proportions of many types of molecules. In technical terms, seawater is a buffered solution, resisting the change in acidity that an increase of carbonates would involve. When some CO2 molecules were absorbed, their presence would alter the balance through a chain of reactions, and in the end some CO2 molecules would be expelled back into the atmosphere. To reach the new equilibrium, Reville now calculated, the water needed to absorb only about a tenth as much gas as a simple-minded calculation would suppose. While it was true that most of the CO2 molecules added to the atmosphere would wind up in the oceans within a few years, most of these molecules, or others already in the oceans, would promptly be evaporated out. Reville could scarcely present that as a new discovery, for the reactions were all tabulated in data known since the 1930s. 25. But nobody had worked out this particular implication of the data. Greenhouse warming had seemed to nearly all scientists a subject of no practical significance. The few researchers who had looked into it had been interested in the oceans mainly because seawater would absorb CO2 on cooling and evaporate it on warming, which might help explain the famous puzzle of the ice ages. People had accordingly calculated how the CO2 content of water changed with temperature. They had seen no reason to take up the problem, which turned out to be quite different, of calculating how much new CO2 the seawater could absorb at a given temperature. Even after Reville made the calculation, its implications were hard to grasp. When Arnold, visiting Scripps in January 1956, wrote about it to Anderson, his collaborator was skeptical of Reville's idea that 80% of the CO2 added to the atmosphere will stay there. He pointed to the uncertainties in biomass uptake. Craig found much uncertainty in such processes, and Reville's insight had scant influence on the other two papers when they were published. 26. Even in Reville's own paper with Sue S., the bulk of the text reflected the pair's original belief that the oceans were absorbing most of the new CO2. The key paragraph, the one that said seawater needed to absorb only about a tenth as much gas as a simple-minded calculation supposed, stood apart like an isolated thought. In the archives it is visibly an addition, scotch-taped onto the original draft. 27. Reville did revise a curve in the paper that he had calculated for the future of atmospheric CO2, finding now that the concentration of the gas should be rising after all. But in this calculation he assumed that industry would emit the gas in future at the same rate as at that time. Few people yet recognized that population and industrialization were shooting up exponentially. So Reville predicted CO2 would level off, a few centuries hence, with a total increase of 40% or less. Public opinion, different ideas were beginning to stir. The geochemist Harrison Brown in particular was sketching out a more realistic vision of a future with exploding population and industrialization. In 1953, he made what seemed like a radical prediction that world population could reach 6 billion by 2050, it actually reached that before 2000. 28. Reville had heard these ideas, and on reflection he understood that industrial emissions were not really constant. Before he sent off the paper he had written with Suez for publication, he added a remark that the accumulation of gas may become significant during future decades if industrial fuel combustion continues to rise exponentially. Keeling's funds. By way of conclusion, Reville remarked that human beings are now carrying out a large-scale geophysical experiment of a kind that could not have happened in the past nor be reproduced in the future. When he wrote this sentence, which has since been quoted more than any other statement in the history of global warming, he was not warning against future perils. He did feel some concern about potential harm over the long run, and had begun to point to the problem in public. But the word experiment sounded benign and progressive to Reville as to most scientists, and in this paper he only meant to point out a fascinating opportunity for the study of geophysical processes. People's attitude toward the rise of CO2, he would write in 1966, should probably contain more curiosity than apprehension. 29. Impacts.